Good day and welcome back to part 2 of our discussion on Newton's method. So let's just begin with a general reminder. Our overall goal is to solve an equation of the form f of x equals 0. That is, find the roots or the x-intercepts of the function f. Now, note I say this is our overall goal. It's not actually what we do with Newton's method. Instead, Newton's method is going to be what we could describe as being an iterative scheme for approximating the root of that function r, and we do so in the following way. We start off with what we think of as being an initial guess. So we somehow guess x1, which we think of as being an initial approximation. So x1 is approximately equal to r. And somehow we come up with this guess. It could be from a graphical exploration, it could be just given to us in the problem. But some initial guess has to be the starting point. Then from that guess, we have kind of this iterative method that we apply. At x1, you can draw the tangent line. Where it intersects the x-axis, we call that x2. And the idea is that x2 is a better approximate to the root r than x1 initially was. Then we play the same game again to find x3, which is an even better approximation. And we can really keep on doing this indefinitely. Once you have xn, which could be x1, you can always find the next iterative using the formula xn minus f of xn, all divided by f prime of xn. We refer to this idea or this method as being Newton's method. I will almost always, whenever it's appropriate, abbreviate Newton's method with just a capital N, capital M. You are more than welcome to do the same. Now, Newton's method is going to create for us this list of numbers. And if this list of numbers converges, that is to say they're getting closer and closer to this root r, we would say that in general Newton's method converges. But immediately you see there's an underlying assumption that we're making. Dividing by f prime of xn really notes that we're assuming f prime of x sub n is not equal to 0. And it turns out there are possibilities where Newton's method, this iterative scheme for approximating the root of a function, will not converge. And as we will see, it more often than not comes down to a good initial guess. So in a sense, this is all really going to hinge upon our choice of x1. So before discussing this problem number 2 together, I would like to ask you all to focus in on this rightmost graph and think about the observation we made above about the derivative not being 0. What would be a particularly poor choice or guess for x1 in this rightmost graph? So hopefully you've thought about this a bit, and I want to show you a couple particularly bad choices for x1. For example, if you were to choose x1 where the tangent line is horizontal, and note the tangent line being horizontal, that would really indicate in this case that f prime of x1 is equal to 0, but we've said we don't want that to occur. And geometrically in our picture, can you see what the problem is? And hopefully you have observed the problem. With a horizontal tangent line, there is no x-intercept, hence no value x2, and this iterative scheme that we have stops. So what's another poor choice? Well, you could just as easily choose your x1 at this other, say, local maximum in this case, where the derivative is 0. And if we look at the graph on the left, we'll see that there's other kind of poor choices. For example, maybe I'm going to guess my x1 is about here. So that seems reasonably close. So we go up to the graph, we draw the tangent line, and where that tangent line intersects the x-axis, we call that x2. Then we go to the graph, we draw the tangent line. Where that intersects the x-axis, we call it x3. Then we go up to the graph, we draw the tangent line. Where that intersects x-axis, we call that x4. And note, we're stuck in this loop where we're just repeating the same approximates over and over again, and we are not getting any closer to that root r that we're hoping to approximate. So the very important observation when it comes to using Newton's method is that it's really important to have an intelligent choice for x1. So we need an intelligent choice for x1. And with that in mind, note if you are using Newton's method and you have to decide upon the x1 yourself, if things are not working out quickly, it may converge slowly, or if it doesn't appear to be converging at all, that's an indication to try a different value for x1. Let's go ahead and explore a nice concrete example. And for an initial example, I think maybe the best thing to do is just some computations. We'll increase the difficulty a bit in our next example. In this example, we're trying to approximate the solution to this equation. That is to say, we can easily identify what's playing the role of our function f of x. And in order to approximate the root, we are going to start off with an initial guess of x1 equals 2. And what I would like us to do is to go through and calculate out x sub 2. In order to do so, we need to know f prime. So if f of x is the polynomial x cubed minus 2x minus 5, f prime is its derivative, 3x squared minus 2. So in terms of our x2, it is going to be x1 minus f of x1 all divided by f prime of x1. F of 2, by inspection, we can see is 8 minus 4 minus 5. So that would be a minus 1. And f prime of 2 is going to be 3 times 4, so 12, minus 2. And this is a problem that we can actually complete by hand. X sub 2 is equal to 2.1. But in general, when it comes to Newton's method, we are most likely going to need a calculator. It's not the type of computations we do quickly and easily in our head. Then x3, the quantity that we would like to find, is x2 minus f of x2 all over f prime of x2. So in our case, x2 is 2.1. So f of 2.1 would be 2.1 cubed minus 2 times 2.1 minus 5, all divided by f prime of 2.1, which is once again kind of that type of computation you would want to do in a calculator. And when I plug this all into my calculator, I get 2.0946. And that's exactly what we've been asked to find, the third approximate x3 to the root of this equation. So x3 is the given number, which completes the example as well as the material covered in this video. In our next video, we'll explore a more involved example with Newton's method. So stay tuned and take care.